Applied Materials just reported the highest quarterly revenue in its history. Revenue reached $9 billion, up 25% from a year earlier, while gross margin stayed above 50%. The company also forecast roughly $10-25 billion in revenue for the next quarter, well above Wall Street expectations. Yet instead of celebrating, investors pushed the shares lower. That reaction reveals something important about the AI boom. Applied Materials is already benefiting enormously from the explosion in semiconductor investment, but investors now expect companies connected to AI infrastructure to grow at an extraordinary pace. Record revenue is no longer automatically impressive if competitors are growing even faster. Reuters noted that Applied Materials' recent performance was being compared with stronger results from rivals such as Lam Research, KLA, and ASML. So what exactly does Applied Materials do, and why could it remain one of the most important hidden winners of the AI race, even if nobody ever sees its logo on an AI product? The answer is that designing an AI chip is only the beginning. NVIDIA can design a GPU containing billions of transistors, but that design still has to be physically manufactured. A semiconductor factory must repeatedly deposit microscopic layers of material, remove selected parts, modify electrical properties, polish surfaces, and build complex structures with extraordinary precision. Applied Materials sells many of the machines used to perform those steps. This makes the company a classic picks and shovels business. Applied Materials does not have to correctly predict whether NVIDIA, AMD, Google, Amazon, or another company ultimately designs the most successful AI processor. If semiconductor manufacturers continue spending billions to produce more advanced chips, Applied Materials can sell equipment to the factories building them. And AI is making semiconductor manufacturing harder in several different ways at the same time. The first is advanced logic. AI accelerators need more computing performance without allowing electricity consumption to rise indefinitely. One way chip makers improve that balance is by shrinking transistors and changing their structure. The industry is moving toward gate-all-around transistors, where the gate surrounds more of the transistor channel than in previous FinFET designs. The exact physics are complicated, but the business consequence is simple. More sophisticated transistor structures require more complicated manufacturing processes. Every additional deposition, etching, inspection, and materials engineering step can increase the amount of equipment required inside a factory. This is why technological difficulty can actually be good for Applied Materials. The harder chips become to manufacture, the more valuable specialized manufacturing tools become. The second opportunity is memory. AI processors are extremely fast, but they become much less useful if data cannot reach them quickly enough. That is why high bandwidth memory, or HBM, has become one of the most important components inside modern AI systems. HBM stacks several memory dies vertically and places them very close to the processor, allowing enormous quantities of data to move rapidly between memory and compute. That architecture improves performance, but it also creates a manufacturing problem. Several pieces of silicon must be connected precisely. Electrical signals must move vertically through the stack, and heat must be controlled inside an extremely dense package. Those challenges require additional materials engineering, advanced packaging, and semiconductor equipment. Applied Materials has said that DRAM and HBM-related demand is becoming an important growth driver, while AI demand continues to support strong spending across advanced logic, memory, and packaging. The third opportunity may be even more important over the long term: advanced packaging. For decades, the semiconductor industry improved performance primarily by shrinking transistors. That process is still continuing, but every new generation is becoming more difficult and expensive. Chip companies are increasingly solving the problem by combining several specialized pieces of silicon inside one package. One chiplet might handle computing, another might handle memory, and another might manage communication. The final product behaves more like one large system, even though it is built from several separate pieces. This approach can reduce manufacturing costs and improve flexibility, but it creates a different kind of complexity. Those chiplets must communicate at enormous speeds, remain precisely aligned, manage heat, and connect through incredibly small electrical pathways. Applied Materials sells equipment used in several of those processes, meaning it can benefit even if the industry eventually depends less on simple transistor shrinking and more on sophisticated packaging. This is an important reason the AI boom is creating such broad demand across semiconductor equipment. AI processors are not just becoming more powerful, the entire architecture around them is becoming more complicated. Applied Materials is also benefiting from another business that receives far less attention, servicing all the machines it has already installed. Semiconductor equipment can remain inside a factory for many years, but chip makers cannot simply buy the machine and forget about it. They need maintenance, replacement parts, upgrades, software, optimization, and technical support. When one critical machine stops working, part of a semiconductor production line can slow down or stop with it. That creates recurring revenue. Selling a machine produces one large payment. Maintaining thousands of machines around the world can generate revenue for years afterward. The more Applied Materials expands its installed base during the current AI investment cycle, the larger that future service opportunity becomes. The company is therefore benefiting from AI in two different ways. First, AI creates demand for more advanced semiconductor manufacturing equipment. Second, the growing installed base creates more service revenue long after the original machines are delivered. But this is also where investors are becoming demanding. Applied Materials' latest forecast was objectively strong. The company expects roughly $10.25 billion in quarterly revenue, above the consensus estimate of around $9.54 billion. Yet shares still fell because investors were comparing its growth rate with other semiconductor equipment companies that have recently delivered even stronger results. That means Applied Materials now faces the same problem as many AI-linked companies. Once investors decide a business is an AI winner, strong performance becomes the minimum requirement. The company must repeatedly demonstrate that it can grow faster than expectations already embedded in the stock price. There are also more fundamental risks. The semiconductor equipment business is highly cyclical. A small number of companies such as TSMC, Samsung, Intel, Micron, and SK Hynix account for a large amount of global factory investment. When those companies expand aggressively, equipment suppliers can experience enormous growth. If they delay new factories or decide they already have enough capacity, equipment orders can fall quickly. Competition is another issue. Applied Materials does not control every manufacturing step. ASML dominates advanced lithography. Lam Research is extremely strong in etching and deposition. KLA specializes heavily in process control and inspection. Applied Materials competes across several categories, but customers frequently buy different tools from different suppliers. China creates an additional complication. Applied Materials has historically generated meaningful revenue from Chinese semiconductor manufacturers, but U.S. export controls restrict which advanced tools can be shipped to certain customers. The company previously estimated that broader export restrictions could reduce fiscal 2026 revenue by roughly $600 million. At the same time, Chinese chip makers continue investing heavily in manufacturing capacity. SIMIC recently reported factory utilization of 93.7%, and has begun raising prices as AI-driven semiconductor demand tightens supply. That creates more potential equipment demand inside China, but geopolitical restrictions mean American suppliers may not be able to capture all of it. This tension shows why semiconductor equipment is strategically important. Governments do not only care about who designs chips, they care about who controls the machinery required to manufacture them. A country can design an advanced processor, but without access to the necessary fabrication equipment, turning that design into millions of reliable chips becomes much harder. Applied Materials, therefore, sits at a critical point in the AI supply chain. The obvious AI winners sell products people can easily understand. NVIDIA sells GPUs. Microsoft sells cloud computing. Meta sells advertising supported by increasingly powerful recommendation systems. Applied Materials sells something less visible, the ability to manufacture the next generation of those products. And the harder semiconductor technology becomes, the stronger that position may become. An advanced AI processor may require new transistor structures. Those structures require new materials. HBM requires increasingly complicated memory production. Chiplets require advanced packaging. More factories require more equipment. More equipment creates more service revenue. This is a business where technological complexity itself can generate demand. That does not guarantee that Applied Materials stock will always rise. The reaction to its latest results proves that valuation and expectations can move independently from the underlying business. A company can produce record revenue and still disappoint investors if the market expected something even better. But the larger business story remains intact. The AI race is not only a competition to design the smartest model or the fastest processor, it is also a competition to manufacture increasingly complicated physical systems at enormous scale. Every new AI chip begins as a design. Before it reaches a data center, hundreds of manufacturing steps must turn that design into physical silicon. Applied Materials gets paid because those steps are becoming harder, and in the semiconductor industry, harder manufacturing can mean a much bigger business.